Thanks for the introduction, Greg. And I'm here from the climate program side of the house to kind of explain ourselves. It's been lovely to sit in with you and hear all of the acronyms and regulations that are not mine. Basically, just to give a sense from the climate regulatory side of what we're trying to do, I work on the transportation side. When I say transportation, I mean the fuels that are used to move people and goods around the state, countries, internationally. Trying to transition onto cleaner fuels is hard. It's hard in every sector. The challenges are unique. It's ideally none of this stuff gets into your laps, but it inevitably will. So just to I'll talk through basically on the vehicle side what we're working on and what we see happening, and then on the fuel side what we see happening. For the state level in the US, our programs mainly are used for on-road transportation because of limitations in how our regulatory authorities work under the US Constitution. In the Canadian programs, they have, the Canadian federal government has a program that's similar to mine, but also BC has one that actually includes the marine sector, I think starting this year or next year. And that's run out of their, I know that their ministry just got renamed as part of the election and the reforming of that government, so I'm going to get it wrong. But I think they're with the Climate Action Secretariat, like the Ministry of Energy now. But anyway, on the vehicle side, where I'll start, we've had a fairly significant ongoing transition to EVs. These are spurred by both state and federal requirements. At the state level, that's our zero emission vehicle and advanced clean trucks programs that are run by colleagues of mine at DEQ. We copy those from the California regulations because under the Federal Clean Air Act, we basically get the option of either we have the federal standards or we can adopt the California standards. And for other states, those are your two choices. It's binary of federal law, or you can do what California does. We had, really significant success with those programs, along with just the industry starting to move over on its own. We're up to, I think California, as of the Q3 data, was up to 24% of new car sales, and that's cars and light duty trucks, or EVs or plug-in hybrids. 23% Washington. Oregon, that percentage is only 15. It was actually higher in Q2, but our rebate for EVs has a very small dollar amount associated with it, and it ran out within, I think, 6.5 weeks, 7 weeks. So basically, we got a bunch of people who bought them in May, and then it ran out, and then that just kind of shifted when people did the vehicle purchases. But the thing that I'll emphasize for this group especially is that these regulations, as they run out over time, will really, on the light duty side, we're expecting to get to near total conversion of the light duty fleet over to either electric or hydrogen vehicles. Some of those will be plug-in hybrids that can still burn liquids. But as I go to my next slide, it's just a really significant decrease in the amount of liquid fuels that will get used. So I pulled California's data and my data because I know where my data is because I'm responsible for it and our forecast, and California's is easier to find, so apologies to their jurisdictions. These are all, and I think California's is in billions of some sort of energy unit. They were doing this for their scoping plan that the Air Resources Board puts out, and they have to do a lot of different energy types. And then you get into the weird units that aren't just gallons or barrels. Mine is, also is in gallons because I just pulled our consumption of liquid fuels from our illustrative mine scenarios. These are projections out through 2045 in the case of California and 2050 in the case of Oregon. These are our best forecasts of what we expect to happen, but the thing that's always fun with forecasts is that they're wrong. You hope that they're useful, but we do see vehicle sales moving in the directions that we would basically get the turnover of the fleet necessary to start seeing these very significant declines in liquid fuel consumption over the next 2 or 3 decades. The one other point I'll just make here, that does mean that we are getting energy from other sources there. That will be Electric engines are a lot more efficient than internal combustion engines. So you use like less than a third of the same amount of energy to move a mile in an electric motor that you do in an internal combustion engine. Most of that will be coming from electricity. There are challenges there. Obviously, in terms of things that end up in your laps, I enjoyed the presentation earlier on the lithium ion fires at sea. That is still like an ongoing issue, especially as we have larger on-road trucks. I know there was an example of one of the Tesla trucks hitting a tree somewhere in California and burning for hours. While I was driving down I-5 to get here from Portland, I went by one of the Daimler trucks, which was thankfully on road and doing all of its normal stuff. But those are very large battery packs. They take a ton of water to put out just because they do consume so much, or they just are so hot when they burn. Stepping over into what I am directly responsible for. So I work on the Clean Fuels program here in Oregon. There are corresponding regulations in all of the Pacific Coast jurisdictions, South Alaska. So BC, Washington, Oregon, California have one. New Mexico is working on getting one regulated. These basically require over time and in a flexible manner all of the fuel suppliers to switch over to some sort of low carbon fuel. This works in conjunction with the vehicle programs to basically make sure that we have low carbon fuels available for that shift. And then for the remaining internal combustion engines, we have some sort of lower carbon fuel, usually going to be a renewable fuel in that case. So that's part of where we're seeing renewable diesel and other fuels that are coming in and taking over those markets, especially on the West Coast. The shift has been pretty pronounced. A lot of people don't notice it, especially with renewable diesel, but California is up to 70% of the diesel fuel they consume is renewable diesel. That's in the bright teal here. There is some biodiesel that still gets used, but that's just a very significant shift. It meets the same ASTM specification as fossil diesel. If you drive up to a 76 station in Oregon, it is renewable diesel now. So if somebody's not paying attention, they're just filling up with it and going about their day, and it burns the same. If anything, it's a little bit cleaner. The fleet maintenance guys tend to like it because they don't have to pull the diesel particulate filters as much with renewable diesel as fossil diesel, because it's just a little bit, has somewhat fewer impurities and just burns a little bit cleaner. Oregon, we're only up to about 35% that's biodiesel or renewable diesel at this point. And we expect that shift to basically go in concert with where California has gone over the next few years as our standards ramp up out to 2035. But it does, one of the key factors here is just the renewable diesel is coming from different places. We're seeing shifts in how fuel moves around at the wholesale level. A lot of that is by rail car, but also we get significant imports that come in from, there's a renewable diesel refinery in Singapore that ships a lot of fuel to the West Coast. That will come in via ocean barges and then get offloaded in Portland, Seattle, San Francisco, or Los Angeles, and then gets distributed out through there. Largely, the pipeline systems don't allow that much of the renewable fuels at this point. So it does mean that it's either moving via rail or barge or truck. And we do see some truck movements between terminals, but most of that's still going to be the last mile out to the card lock, fleet, retail station. It also means that these refineries are pulling in different feedstocks now. A lot of them have started, especially along the West Coast, moving into either co-processing the renewable feedstocks from plant oils, animal tallow, and used cooking oil, along with crude oil. So they might have somewhat less crude oil shipments in the future, more of these different types of oils that are coming in from biological sources. Cherry Point's been doing this for several years now up in Washington, where they have a diesel unit that runs, I think, up to like 30+% of biological feedstock along with the crude oil. I know U.S. Oil in Tacoma at that refinery is starting to also do that. But we've also seen just wholesale refinery conversions. There's a couple ongoing in the Bay Area in California. There's several out through the Mountain West where there were smaller refineries that had poor economics, and they just decided to make the leap over to renewable fuels, either from like the entire unit, or they just took one of their diesel units and switched that over to renewable diesel. And largely, when it's inland, those shipments come in via rail. So we just see a lot more diesel fuel moving by rail. It also means, especially when you combine that with just the outlook for on-road diesel consumption, on-road gasoline consumption going down over the coming decades. You do see a number of refineries that may have always had not great economics that are looking more towards closing. I know Phillips 66 has announced the closure of 2 of their Los Angeles refineries in Q4 of 2025. And it's likely that we'll also see other refineries like trying to figure out what makes sense for them in the next decade or so. Renewable diesel has been well figured out. On the gasoline side, it's still mainly just ethanol that gets used. There's not really a great technology that's come to bear on creating a renewable gasoline. It's possible that will get figured out. One of the things that I always say about my program is that I expect to get surprised. We don't have a perfect crystal ball. We don't know what people will come up with in terms of the technology. So we're trying to be adaptable and figure out what will work, what has an actual low carbon benefit that we can stand behind when we apply our science to it. And I could go into a ton more acronyms and details there, but I know how lost I am when I hear about all the acronyms you guys have, so I was trying to keep this a relatively high level. I'm happy to take questions. I'm happy to explain myself. I'm happy to see what trends we're seeing, what questions we're getting in on the climate program side of things. But yeah, thank you for having me. It's been really interesting. It's nice to get a day out of my normal world.
Yeah, thanks for being here. That was terrific. I drive past the Phillips 66 tank farm in the Bay Area, which used to have the big orange 76 ball. Now it's a big green 76 ball because it's all renewable. They've converted completely over. And as you hinted at, there are great things about us using renewable fuels, of course, but if you are a renewably oiled bird versus a petroleum oiled bird, the physical consequences are the same in terms of thermoregulation and degradation of feathers and ability to fly. So there's a lot of things going on there that are still challenges that we need to address moving forward. Any questions for Bill?
There's a question on the chat from Trevor that he asks, do you anticipate renewable diesel growth beyond the West Coast states?
I do. We're seeing a shift towards it. In the absence of supportive federal policy in the US, it's harder to see it happening if the states inland or on the East Coast are not also adopting clean fuels policies. Basically, my program and the programs that me and my sister agencies run in the different states just create clear economic drivers. It's like between 30 to 40 cents per gallon to run those fuels, and it creates a disincentive to using the fossil fuels. So, this is a market-based program. I didn't go into all the jargon because I have a ton of jargon, but without those kind of incentives and drivers, it'll happen less. I know from talking to people inland that they just can't get the fuel because it all just goes to the West Coast because that's where the economics are. Canada has a federal program, so I would expect it to hit the inland provinces as that program ramps up. It went into effect in 2022, and their targets are increasing over the next few years. That would likely drive at least some of the diesel pool in Canada shifting.
Good question. Do you see a upper limit on biofuel availability? There's only so many cows on the planet that you can turn into fuel.
Well, and the cows really aren't or help from the plant oil side of things, because usually what happens is you express the oil for renewable diesel and then the leftover soybeans get used for animal feed. So there is an upper limit. It's hard to know exactly where that is, but at some point you're using so much biofuels that you have to convert so much land to farming that it just doesn't make sense. So that is in part why I was also pointing to the decline in overall liquid fuel demand. If you're not doing it with that kind of decline in overall liquid fuel demand, it will not be sustainable to shift to biofuels. We couldn't just take existing US or North America fuel demands, switch it all to biofuels and have that work out. So it does need to be in concert with either some really significant efficiency gains or switching over to different energy sources. Electricity is what's really been proved out as working, at least within its own set of headaches. We do have hydrogen out there. We're still at an early stage for how much that gets used. There's a fair number of those fueling stations in California, and that's basically where the only ecosystem exists for it. The earlier discussion was around methanol, but you need that same thing for road fueling. So, and hydrogen is a pretty tricky molecule to keep contained. So we'll see what plays out there, but electricity has been moving pretty quickly so far.
Thank you.
Yeah, thanks, Bill. Appreciate that. And definitely, yeah, some really interesting follow on there. We could have a whole another hour talking about the conversion, competition of land for food production versus energy production and that sort of thing. So appreciate that. Our next presenter is going to be talking maybe in this context a bit of as we make transition from petroleum, traditional fossil fuels to renewable fuels, making fossil fuels more sustainable. Our next presenter is Dr. Robert Farragher. He is a research scientist with more than 10 years experience at Environment and Climate Change Canada, residing in Ottawa, Ontario, in the environmental field of chemical and oil spill research and development. His specialties include environmental emergencies and enforcement and spill treating agents. R&D efforts have focused on the advancement of detection, developing new test methods for the evaluation of surface treating agents, and determining fate and behavior for new petroleum products or from environmental spills. He is part of a team whose mandate is to undertake R&D, develop spill response tools, and to provide scientific advice to federal government scientific support coordinators during spills. Now, Robert, we really appreciate you being here. Special thanks to Robert, who is on the East Coast, so he is spending his evening with us. Thank you so much, Robert. Take it away.
Thank you very much. I'll just get in presentation mode. Just give me 1 second here.
No worries.
All right. All right. Oh, I don't think you can, my bad.
Yeah, if you just go up to display settings, I think it'll let you switch to, there you go. Perfect. Thanks, sir.
All right, no problem. As it stands right now, I'm last, but that's okay. They always say, hold the best for last. I want to thank everyone for staying in, for the day, and especially at this later hour. Before I begin, I just want to say that acknowledging that I'm speaking from the traditional territory of the Algonquin people, specifically the Anishinaabe Algonquin Nation. And so for my talk, it's a little bit different than what everyone else has said and gone through. We're looking at the new alternatives for the heavy fuels or the intermediate fuels that are used within the shipping industry, going to the low sulfur versions. For the very low sulfur, it's about 0.5% part, and then the ultra low is typically 0.1% sulfur, which is a lot reduced compared to what it originally was. And a lot of my talk is going to be focused on doing the discussing the differences between them, and then how that kind of impacts a spill response. And so just a quick overview. I'll try to be brief. From the IMO, they introduced the implementation of the low sulfur fuels back in January 2020. And that came through the MARPOL Annex 6. And really it was about emission control areas. They wanted to reduce or improve the air quality. So they wanted to reduce the NOx's, the sulfur dioxides, the particulate matter, because air quality has a significant impact on health. And a lot of these fuels are proposed to be used in the Arctic regions or the polar regions. And from here, going to be talking about the guiding principle behind the properties for these fuels, which is the ISO standard 8217. And then quickly talking about the first large scale spill of the VLSFO, and then the rest of it of my talk is just the physical properties, the differences between the fuels that we have known and what we're currently dealing with these low sulfur fuels, and impacts to spill response. So here's a table that's been pulled out from the standard itself. It's dealing with the residual fuels specifically. And so you can see the residual marine, the RM, and then the A through K just talks about A meaning light, K meaning a fair bit more heavier. And so, a lot of these numbers are based on the viscosity measurements at 50 degrees. So a lot of people may be familiar with an IFO 180, and so that's what you're looking at here. So the 180 is the viscosity at 50 degrees. And so when we're dealing with spill response, some of the key factors that we're interested in providing to a spill responder are viscosity, so the tendency for the material to flow on the surface, so how big of an area the oil or the fuel is going to be. Density, simply, is it going to float or is it going to sink? And that has implications on spill response. And lastly, keeping it simple down to just 3 components, pour point. And then what state is that material going to be when it hits the surface of the water? And a lot of the fuels being used, they are used at 50 degrees within the ship or close thereof. And brings me to the first real big spill of VLSFO. Now you have to remember that the IMO introduced, having ships to use low sulfur fuels January 1st, 2020. By July, we had our first incident in the French island of Mauritius, so a tropical area, and we had the marine vessel Wakashio. And so he essentially hit a reef close to the island, eventually broke apart, spilling approximately 1,000 tons of oil. And it was, at the time it wasn't known, but it was determined to be a VLSFO. And I'm not going to dwell too much into this incident. There's a lot of presentations that have gone into the spill and the complications, especially undergoing a spill during COVID. So what some of the lessons that were taken away was that each one of these blends of VLSFO is different. They have different producers, they have different feedstocks going in, and that all changes how these behave. Also complicating this spill, all of the hydraulic and lubricating oils that came in. And some of the key takeaways from this spill was that we have to keep applying our learning, and this knowledge cannot be, we can't do ivory towers. Like, these have to be shared so that the spill community can learn from all of these lessons and then be better off for it. And now it brings me into just looking at the physical properties of some of these materials. Now, these are the ones that we have that have come into our lab. And this is some data that's that I'm sharing today. If you want a lot more detail, we do have an open database. And so you can go to that location and get a lot more data. And a lot of the spill responders, spill modelers use this data for assisting in spills. But so with the truncated information that I'm presenting today, with the VLSFOs, again, density, viscosity, and pour point. The one thing I just want to, show is we have a very, very broad range here. We have essentially 0.88 for our density, and then we go up to almost 1. But the big grand scheme of things, for a spill response, it's less than 1, which means that it's going to float on water. So all of these materials will float, and we're not going to be dealing with a sinking substance right in the beginning. Now, viscosity is another a very, very different component to these fuels. As you see here, we can have anything, well, we have 1,000 centipoise or 1,000 millipascal seconds, but then we can go up to, essentially over 1,000,000. So we have 3 orders of magnitude difference in that viscosity, and that has a very big impact on how it will spread and spill in an open water system. And then lastly, looking at pour point for these materials is they are very, very broad again. So you can have something that's liquid when it hits the water, or like a lot of these, they have temperatures that are well above 0. And so when they hit the water, they become solid, which then impacts how we are able to move forward for spill response and dealing with them. And the sulfur content is included to show that it isn't compliant with the ISO standard, except the ultra low sulfur fuel, which is slightly above. But I just want to compare this to some of the other the heavy fuel oils or the intermediate fuel oils that have previously been known. Densities are very close to one another. Viscosities, again, they are close to one another, and the pour points are all liquid, typically in most spills. And I want to bring up this next graph, which shows the boiling points of a lot of the components in the fuel. So all the hydrocarbon components are able to be shown with a simulated distillation, and it really emphasizes how different some of these materials can be. So I have here 3 traditional fuels, an IFO 120, 300, and then an HFO that we have at Environment Canada. And we have 9 VLSFOs that have come in. And I have several areas that I want to really focus on. The first one is this front end. So these are very, very light materials. They, they start evaporating very, very quickly and, and rapidly. And then they finish off, with all the others. Now, most of the materials, they all start evaporating out at the same time. So, something that you would typically expect, but everything differs once you start removing those first lighter components. The second one I want to bring up is this sample number 3. Now, this one's very different. It ends, I hope you can see my mouse moving, but this starts the last. So it has the least amount of volatiles, but then when you look at it, it finishes well ahead of any of the other ones. So it has the narrowest range of all of the materials that we've seen for any of the VLSFOs or any of the traditional fuels that we've encountered before. Next, I want to bring up, this one. So it starts off all nice and, where everyone else is, but it has much larger components, comes off very, very slowly. And, between all of these fuels, there's a huge difference in boiling points for a significant, range going up. So at about a 10% mass loss, we're looking at about 200 degrees difference between these fuels. And that's maintained up until about 80%. And, it's just very, very strange to have such a broad distribution of hydrocarbons within those materials. And lastly, I want to show that these 3 materials here are what were the conventional fuels. So very, very different properties and very, different viscosities of them. And you can see here, the blending that did occur. So you can see very, very, very light components, a plateau, and then here's where the residual components of, getting that last part of the distillation, that bottom of the barrel, blended in and then used for a fuel source. And here, even though we have very, very different properties, they have it's a 50-degree boiling point difference between those materials. So very, very different. And I also want to point out the fact that these materials all come from the same feedstocks. So here we have almost everything coming off for our distillation. So what's implied here is that these materials are engineered at the refinery. They are blended with different additives and blended with different other components to have these differences. And that impacts how they will behave within the environment. And the next slide is how to show you just how different a lot of these materials are. So we have the red here, or the orange, and this is typically what you would expect for your conventional fuels, your IFO, HFOs. And so when you're looking at this, because it's a graph of viscosity versus pour point. So here you had your IFO 300, IFO 180, and you could expect to have, your certain pour points. And there is no blending of these fuels over into, the type of properties that we're experiencing or seeing with the VLSFOs or the ULSFOs. And I do want to point out that this is from the Norwegian Coastal Administration, and we are involved with some collaborations with them. And so you can see here, especially with the VLSFOs, there's a huge difference from like -15 up to 30 of expected pour points. Very, very broad, huge broad range, and just not your typical expectation for a fuel that's typically used in the shipping industry. And then especially looking at the ULSFOs, they're all very, very high. So you go from, your ship to water, your temperature is not going to be 30, that's more tropical. And so we're looking at 15 or below for any of the waters that are typically associated with Canada in the northern United States. And then that has very big impacts for spill response. And just try to, why aren't you moving? Sorry about that. A little slower. And so just a quick, very, very quick here. So at 50 degrees, this is where we're operating within the ship. This graph is just viscosity versus temperature. And you can see here that some of the materials, they trend up a little bit for viscosity over temperature. But you can see here that the ones that are, that have a much higher pour point, you can see this very drastic change in temperature when we go from a liquid to a solid state. And again, that has impacts for spill response. Now, I'm drawing in a lot of information from some of our other collaborators and people that we are in communication with. So they were doing, some research on some spills within their environmental chamber. And so you can, again, just how different some of these materials are. You can see here a very, very light one, spreading out as you typically would expect. And then you get a fair bit thicker material, and then you get this solid material when it hits the water. So when we get a call for responding to a spill of VLSFO, we don't know what actually we're going to have to respond to. So that, moving forward into spill response, we need to look at being able to have a very, very broad, diverse source of spill response tools to be able to address these issues. Now, some of the things that we look at for fate and behavior are emotions. So I'll try to be quick on here. Now we do these emotions in a standardized fashion, and we also do evaporation on these materials in a standardized fashion. And one of the complicating things when we're dealing with spill response is emotion formation, because that changes the volume of the material as well as how it can be used for dispersants or other means to, for skimmers and what have you. So one of the things that was found with all of the first 4 VLSFOs that actually came in, regardless of how much we evaporated from the materials or in a specific quantity, whether we started at our fresh, a little bit of evaporation, or even went into some of the, more evaporated states of the material, these four materials all formed emulsions. So that, would complicate spill response. And it was very odd to have them all form emulsions, especially since some of them, the lighter ones that I showed you from before of the simulated distillation, was essentially they had a basically they were water. So they had a viscosity very, very close to water, and something that just you weren't expecting. Now, with these emulsions, we've monitored them just because all of this material is new. We've monitored them for over a year. So you can see here, so the big takeaway from here is the conventional fuels, they on the measuring the viscosity of these materials, they stopped at a month and then they plateaued. However, when we were looking at these the emulsions at 15 degrees for the fresh, or having a lot more lighter components of these materials, when it came to looking at over time, they continued to change. So these materials are not they're not behaving the same way as our conventional fuels, and so this is just something to keep note. Now, when we moved to 0 degrees in monitoring, we found that that change was more pronounced, and especially for some of the materials that didn't really move very much, we had a much greater viscosity change, and so these materials are changing more and more over time. And we're coming up to 2 years, and it's just going to be interesting to see what these materials actually turn about to. Another spill response strategy is looking at dispersibility. All of these tests are done with corrects at 9500. Just for a lot of these materials down here, typical behavior, temperature and evaporation on the material, you start high and you go lower. Except these few up top. So these lighter ones, excuse me, it didn't matter how much we evaporated or at what temperature, whether it was 15 or 0 degrees. They had an amazing window of opportunity. But that's not typically known, especially it becomes not an option once you start emulsifying the material. Now, looking at other spill response options, I do realize my time, I'm going to try to hurry, is looking at skimmer effectiveness for once these materials are spilled at sea. And again, this is from the Norwegian Coastal Administration and some of the work that they've done. And so, looking at skimmer options, they found, there weren't a lot of great options for being able to remove these materials. And part of the problem that they found with using skimmers was the skimmer would possibly be functional, be able to remove the oil, but then the pump wasn't functioning. It wasn't able to continue to remove that material from that reservoir once the belt or the drum, or well, in this case, you see that the belt wasn't viable. And so these materials provide a very, very challenging environment to be able to deal with them once they get spilled in the environment. And as well, and it also depended whether you were in a static system or a dynamic. So if you're out at sea moving, then you're able to actually have much better response. But if you're in a harbor, very, very calm environment, you had less efficiency for being able to move forward effectively using skimmers for your response. Also, some of the information that came about from this study is that in situ burning is not an effective strategy. Sorbents do not work. A lot of it because of the higher pour points, they just don't adhere. You can't absorb a solid to another solid. So it prevents a really, really big challenge for dealing with these spills in a marine environment or any water environment. And now, I don't know how many people have actually poured hot butter into water, but that's a very good analogy for being able to move forward with some of these VLSFOs. So here is some work done with the Ameros project. You know, it's all available on YouTube, so you can go see a much more thorough explanation of some of the work that was done. But essentially, this is what you're looking at for some of the higher pour point materials being spilled into water. There's not a lot of cohesiveness with it. They're clumpy. And so you can sort of see why some of the spill response options that we typically have used in the past don't work. And one of the sort of provided, or what came out of the Norwegian Coastal Administration for the Ameros project here was, is this an effective strategy moving forward? Physical removal. Some of the, because of the failures of the skimmers, backhoe loaders were proposed as being the most efficient way of removing these materials. And so briefly, for spill response, emulsification will complicate a spill response, not only, with greater volumes, but also if left out there, natural attenuation is decreased. The application of dispersants, you could have an amazing window or, your typical response. Now, how do all of these VLSFOs, correspond to all of the spill modeling software that we have? That's sort of a debatable, I talked to our spill modeler in-house, and that's, it's a bit of a question. And so it comes to, how do we move forward with cleanup strategies? The skimmers and booms, the pumps, just these booms might be the best option going forward. Skimmers, there are a lot of lessons, to be learned going forward. Things aren't as effective as we have known to be in the past. And essentially any spill that does occur, essentially go out with as much equipment as you possibly can, or know people where you can draw from. And in conclusions, marine fuels will be spilled, but we need to know how these materials are. So we need to be able to characterize them in order to know what we're going to be dealing with. A huge broad range of physical properties with these materials. Emulsification, again, like it's whether it's 0 or 15 degrees, these things formed, and they are incredibly stable. So, if they get trapped in ice, they're going to be moving around. And so that challenges a lot of things. With looking at the ISO standard 8217, they're coming out with a new one, this year. And so that's going to, change, possibly looking at additives and blending components for these materials. And again, we need to know how to deal with these materials in order to be able to remove them, because they're being used on ships. We need to have strategies for not if the spill is going to happen, but when. And at this point, I just want to say thank you very much for, having me go a little bit over, not stopping me. And I thank you very much for your time and any questions.